In the examples we did a few moments ago, we talked about forces doing work where the forces did not change with position, like gravity, the mg gravity, or like friction. But there are some forces that do change with position, like springs or the universal law of gravitation, and you can't handle them in quite the same way we did. Remember, the energy principle says E final minus E initial is equal to the work done by external forces. That's equal to F external dot producted with delta R. Okay? Now, in the cases we did, the external force didn't change. We could just change this to some macroscopic distance. It didn't matter because this doesn't change as we do this. But if this is a function of the position, then we have to take into account how that changes as R changes. So we could, suppose we wanted to have a system change over some macroscopic distance, we would have to say that delta E is equal to the sum over all the small steps delta R sub I of F external dot delta R sub I, realizing that this is a function of the position. Whenever you do a sum, you're starting to look at something that looks like integrals. In the limit, where delta R goes to 0, we could write delta E is equal to the integral of F external dot producted with dr from the initial position to the final position. And this is a very useful way of putting it. These two are equivalent. This is the way you input this into a computer if you're trying to calculate changes in forces that are changing, calculate work from that. This is how you do it if you don't have a computer but you have some functions that you can integrate easily. The simplest type of function I know of to integrate in this case is the force exerted by a spring, minus kx. So let's just see how that works out. Suppose I take a mass on a spring, and the spring has a spring constant kx. And I'm going to use an external force F sub x, ext, just pretend it's my hand, and I'm going to take my hand and I'm going to compress that spring a certain distance. Let's start off at x is equal to 0 and compress it till I get x is equal to d, just to put some values in. Okay. I want to know how much work do I have to do to move this mass from there to there. Okay. Once again, I always have to draw out a force diagram and label the forces. The forces acting on this mass are the external force and the force that the spring exerts. So I've got the mass, the force of the spring, the force of my hand, this external force here. I'm going to presume that I do this at a constant, I move this at a constant velocity. So I'm not trying to accelerate the mass, I'm not trying to hit it, make it back and forth. I'm just going to move it at a constant velocity from the equilibrium point to that point. Okay. Since I'm moving it at a constant velocity, that means the change in momentum in this mass is 0. So delta P over delta T is equal to 0. That implies that the external force minus the force of the spring is equal to 0. And let's see, the force of the spring is equal to minus kx, and that means the external force I have to exert is equal to plus kx, where this is the plus x direction. Okay, so let's see if I got everything I need. I've got the diagram, I've got the forces that are involved, I've written down the momentum principle to help me keep track of those forces, and I wrote what they were. Okay, so the question I'm going to ask is, or I have asked is, how much work must I have to do to compress that spring from here to here? Okay, and I just figured out the force I have to exert at any time is kx. So let's see. I'm going to erase this lower part. And I can say that the final energy of the mass minus the initial energy of the mass is equal to 1/2 mv final squared plus 1/2 minus 1/2 mv initial squared is equal to the sum of the forces. That's equal to F external minus F spring plus F spring, and I took care of the minus sign by the way I wrote F spring. If I do this at a constant velocity, mvi is equal to mvf, so this term turns out to be equal to 0, and all I've proven out of that is that F external is equal to minus F spring, and that's equal to kx. We already knew that. Okay? Let's look at all we've said here is that the total work done by the hand pushing and by the spring, they end up being 0. Okay? The work done by the external force is going to be the integral of the external force times dx, that's the motion we're doing, from x is equal to 0 to x is equal to d. Okay? As I push this, I'm going to have to exert more and more force as I move it along. It takes no force to get it started, and then the more I compress this, the force that I have to exert is going to be greater. It's going to go as kx. So this is equal to the integral from 0 to d of kx dx, and that's equal to 1/2 kx squared evaluated at 0 and d. And so the amount of work the external agent has to do is going to be equal to 1/2 k times the distance squared that I've compressed the spring. Okay? All right, now since the total work done on the system was equal to 0, I should have written this as the work done, and that's the work done. Excuse me. The total work done on the system is equal to 0, so the work done by the external agent is plus 1/2 kd squared. The work done by the spring is equal to minus 1/2 kd squared. Remember, if I've got a d squared, k is always positive, d squared is going to be positive. So this is intrinsically positive, and the work done by the spring is opposing the motion, so I have negative work for the spring. Okay? So that's the simplest example I know of calculating the work done with a changing force.